Welcome to Complexity Made Simple. And in this video newsletter, well, I'm going to welcome you to video 1 of the Catapult case study. Because what we're going to do is this. People have been asking me about doing something like this. We're going to do a complete project case study on this Catapult. So we're probably going to do about 10 or 12 videos all told, where we take this process from chaos to control and from control to excellence. I'm going to show you how to use DMAIC. I'm going to show you how to use DMAIC twice. One to get the process under control and one to take the process to excellence. So that's what we're up to. We're going to do a case study and we're going to take this from chaos to control to excellence. So this is video 1. This is the introduction. So it's the Catapult. It's the Catapult case study. And in this video, step 1, what are we going to be doing? We're going to do define and measure. So those two, they have to come together. So we can't do define without doing some measurement. So you can't just do define on its own. It makes no sense. So if you're in a company where they're very anal about doing this step first, then this step just makes no sense. So first thing is, we're going to define the problem. Now we're going to assume that I've been given this process and I've been told that it's got a massive defect rate and it's my job to get rid of it. So the first thing we got to do is define the state of the problem, and we're going to do just that. So we're going to do the define and the measure together, because I have to collect some measures to find out what the problem is. So I've got a large defect rate, don't know too much about it. So here's the first thing I'm going to do. I'm going to run the process hands off with no adjustments, and I'm going to run it, in this case I'm going to run it 24 times, but actually what I'd want you to do is to run the process probably 50 times. So walk up to your machine, switch it on, make 50 pieces straight into your hand, and then measure the quality feature of interest. So that's what we're going to be doing. So I'm going to be firing 24 times, and then we'll come back and we'll define the nature of the problem. Okay, so you can see me here in the video. I've set the Catapult up. I'm going to follow some certain rules. So I'm going to make sure that I don't move the pegs on the machine, so the settings won't be adjusted. I'm going to pull the Catapult back to the same angle as well as I can. So I'm pulling it back to 177 and all the pegs will remain set as they are. And we're trying to follow a cycle time of 1 every 15 seconds, because that will meet our customer demand and keep our customers happy. And I fire 24 times. So you can see me doing that now and collecting that data. For you, 50 data points of the measure of choice. So there's the original data. Now here I am, I'm showing you the results. So here's the results we got from that exercise. And at the moment, of course, they're just numbers. They're not really telling me anything about the problem at all. So define still can't be done here. Now my customers want me to land the ball in a tolerance of plus or minus 3 inches. So I'm supposed to land the ball in a range of just 6 inches. So let's take the data, do some analysis and see how we're doing. Now the first thing I'm going to do is I'm just going to plot a graph. Now in this case I'm going to use a pen and pencil, and you can see the graph here and you can see the range. I'm supposed to have a range of 6 inches. You can see the maximum, you can see the minimum. I've got a range of 43 inches. Clearly we have a serious problem. Now in order to define the problem with a little bit of numbers, we're going to go to something a little bit more technical. I'm going to go to Excel. We'll put the data into Excel and we'll get some analysis using the histogram and the CPK analysis as well. So let's take a look at that now. Okay, so there's my 24 data points. I've got them into Excel, and I've also got my Sigma Zone software running, so I can use some statistical tools here. Sigma Zone, very simple add-in into Excel, great piece of software. So first thing I'm going to do is I'm going to repeat the run chart that I did by hand. So let's just go and pick a run chart. That's the one I prefer. Okay, now you can see the chaos. You know, are we in chaos or are we in control? This is for the same setting. Nothing was supposed to be changing on the machine, and yet I got a 43-inch range. Okay, so there is graphical analysis number one. So the first thing to say is it looks like we're in chaos. So let's go and do graphical analysis number two. So I'm going to do a histogram now. Okay, now there is the histogram. Now obviously the histogram is the distribution of that run chart, and I've got some summary statistics up in the top left hand corner there that are telling the tale. I'm sitting at an average of about 68 inches, but I've got a standard deviation of 10, which if I multiply that by 6 gives me a potential range of 60. Now you can see the histogram going from 30 at the bottom all the way from 90 at the top. I'm supposed to get those results inside a range of 6. So I'm 10 times worse than I actually need to be in terms of my capability. And now we'll do the capability diagram that just makes that point as well. So Sigma Zone, analysis diagrams, CPK. I'm going to suggest that 68 is the right target. So I'm going to go +3, which takes me to 71, -3, which takes me down to 65. Click finish. And there is my capability. So the problem I have, the physics of the problem, is I have too much variability. It's chaos. There's nothing the operator can do about this. They could wiggle that diagram backwards and forwards, but it wouldn't make any difference to the defect rate except make it worse. They can't make this process any better. All they can do is set it on center, take their hands off, drink tea and read the paper, and then they would get that minimum defect rate that you can see there, which is basically 769,000 defects per million, 77%. Okay, so I've got a defect rate of 77%, far too much variability. That's the physics of the problem. So now we can enter that into my project definition sheet. So here we are. Let's just put some basic details in there. Who's the expert working on this? So the project title, Catapult. Defects. I'm going to keep it simple. Now the problem statement. So what's the statement of physics? That's all we need to know. Do I have too much variability, or is my aim wrong on my process? So problem statement. Too much variability. I have a standard deviation of 10, and I have a defect rate of 77%. Okay, there's the problem statement. Now down here, the cost of poor quality, I'm going to suggest that I make 1,000 a week. 77% of them go in the bin. So I'm going to suggest that each one costs me £1. So cost of poor quality, £770 per week. I'll put that in there. What's my objective? My objective is standard deviation equal to 1 inch. That would give me a CPK equal to 1. That would be the minimum that we would want. I'd like to be better than that if I can, but that's the objective I'm going to set. At least I've got a chance of being defect free. What's the process? It's the Catapult. Who's the process owner? Allen and Partners Limited. Champion. Now, of course, what does a champion do for you? I don't need to fill these in, but your champion removes roadblocks. Maybe finds a little bit of cash for you to do some special maintenance, that type of thing. Arranges for overtime when you're doing tests on the machine, that type of thing. And of course, I don't have suppliers or customers, and I don't have a team in this case. It's going to be me. But the sorts of teams, who would you want in a team? You would definitely want an operator. You would definitely want a technician. You would definitely want a maintenance technician. In other words, you want doers, people that touch this machine all the while. Okay, so there's the problem statement. It's a statement of physics. Is the problem too much variability, or is the problem aim? In this case, I have too much variability. It doesn't matter what the aim is. I cannot get the results to fit inside the tolerance. There is your define. Now I'll just show you a quick example of a case study where someone has done exactly this. They took 40 data points, plotted the same sorts of graphs, and you can see whether they've got too much variability or a problem of aim. So here are their 40, these are 40 data points. They haven't touched the machine. It's consecutive parts, and you can see that without touching the machine swings from low settings to high settings. It's got too much variability. We've got to get in and do something about that. There's the run chart. There's the histogram. A little bit lumpy. Often when you've got chaotic processes, you don't get a very normal result. And then we run a CPK. And the CPK, look, process is sitting dead center, but we've got those tails. And the operator can do nothing about the tails. They can swing that picture backwards and forwards if they want, but they won't make the defect rate go away. They should center the process, sit back, drink tea and read the paper, and that's the best that the defect rate will ever be. It's actually at 10% in this case. You can see it up here, look. There's the 10% defect rate. So that's exactly what we've done on the Catapult, and there is effectively step 1, define and measure, completed. Okay, so there's step 1, define. Is my problem about too much variability, or is it about aim? The problem is about too much variability. Now I know that. I know which tools to use next. Now what we're going to do, we're going to continue with the measure function in the next video, because I'm going to talk about measurement system analysis, and you could tell from the measurement system in the video trying to spot where the ball landed. Not a great measurement system. So the measurement system's got to be improved before we move forward. I'm going to talk to you about MSA in the next video. But now I know there's too much variability, I know which tools to pick. MSA is going to take the variability out of the measurement system. Process flow, cause and effect, is going to identify the variation in that piece of equipment that we can tackle and try and squeeze in the variability. But that'll be in video 2. Video 2 will be all about measurement system analysis.